Welcome to the course on VLSI physical design with timing analysis. In this lecture, we will discuss about PDK and other files used in VLSI physical design. So, the content of this lecture will discuss about the characterization of the sequential cells we have left out in the last lecture. Then we will discuss about different files available in the PDK, for example, LEF, DEF, ITF and PDK related files. So, first of all we will discuss about the sequential cell characterization. So, it has 3 parameter, one is called setup time, second one is the hold time, then the third one is the clock to Q delay, clock to Q propagation delay. So, let us say I have a flip flop. Okay. So, the main thing what I am explaining here is that how we can do some spice simulation and find out the basically setup and hold time. Clock to Q delay is very easy. So, I will not discuss clock to Q delay. Basically, I will discuss about this is the clock pin, this is the D pin and this is the Q pin. I have a clock is there. Okay. I have this is the clock, I have a D. So, the arrival time of the data I am changing. So, first time the data will arrive here, I will run a spice simulation, then I will change the arrival time of the data like this. I will change the arrival time in another spice run like this. So, let us say 4 point, what I will do? I will find my clock to Q delay. The clock to Q delay is basically it will take some time to basically find the Q value after the rising edge of the clock. Let us say till rising edge, okay, it will take some time, let us say like this. So, this is corresponds to the first edge, this is corresponds to the first edge. So, this 50% to this 50% is clock to Q delay. When the data is at a long distance from the clock edge, your clock to Q delay is some value, let us say x. So, now what I have to do for the edge 2, again I need to find the clock to Q delay. For edge 3, again I need to find the clock to Q delay. Then edge 4, again I will find the clock to Q delay. So, what I am doing is that my x axis is basically, let us say I am plotting, y axis is my clock to Q delay and my x axis is basically data to clock distance, okay, data to clock distance or duration. So, when the distance is large, my clock to Q delay is constant like this. When the data comes closer to the clock edge, then the delay starts to increase actually, and finally it will never capture by the flip flop. When the clock to Q delay is degrading, so we are taking, let us say this is the delay of D naught, when my delay is increased by 10%. Okay. So, when the delay becomes, let us say 1.1 D naught, 10% means then the corresponding D to clock distance is your setup time. This is your T setup. Similarly, we have to do the same procedure for hold time, but we have to do it from the after the rising edge of the clock. So, this is the procedure for finding the setup and hold time, and obviously you learned how to find the clock to Q delay, basically 50% of the clock edge to the 50% of the Q output, how much time it takes, that is your clock to Q delay. So, this figure is basically showing that the setup time is found to be 0.21 nanosecond and your data is captured properly. When it is 0.20 nanosecond, your data is not captured properly. Hence, the setup time is 0.21 nanosecond. Now, we will discuss about this nonlinear delay model. Nonlinear delay model says that whatever we discussed so far, we are finding the cell delay. Your one direction is your input transition time and another direction is basically your output capacitance, and for each of these combinations of some tables, here in this example we showed some table, but it depends upon your requirement to create those points and the to do the characterization, but that combinations you will find the propagation delay and the transition times. So, if that point whenever I am going through the timing analysis tool and that point is not available in the basically in the table, then what it will do is that it will interpolate using some linear or nonlinear interpolation technique to find out its value. So, this is popularly known as nonlinear delay model or NLDM model, which is used extensively in industry to do timing characterizations. So, here this NLDM tables for the sequential cell will contain setup time, it has a rise constant and the fall constant, okay. Then the hold time, it has a rise constant and the fall constant, okay. So, there will be 4 table corresponding 2 table corresponding to the setup time and 2 tables corresponding to the hold time. Similarly, the clock to Q delay is basically a delay parameter. We should have cell rise, cell fall, okay, and we have rise transition time and fall transition time corresponding to clock to Q delay. So, here you have 4 tables corresponding to clock to Q delay. Similarly, for asynchronous inputs, we have such as reset and set, we have 2 more timing parameters are there. One is called the recovery time and removal time. We will discuss about this recovery and removal time in the in this lecture. So, if you can see here we have the sequential circuit is there like D flip flop or latches or anything. So, you have different timing arcs are there. So, if you can see you have a clock pin and a Q pin, you have a propagation delay, you have rise and fall propagation delay. Similarly, you have clock to data pin, you have setup time which is rise and fall. Similarly, hold time you have rise and fall, and with respect to the this asynchronous input like reset, you have recovery and removal time. So, whatever I discussed, setup time is defined as the time before the rising edge of the clock, the data should be available such that it will be sampled by the flip flop properly. The hold time is the time after the rising edge of the clock, the data should be stable this time such that it will be captured by the flop properly. So, this is your clock to Q delay, the 50% of the clock to the output pin. So, the recovery time is the minimum time, okay, that a asynchronous input should be stable after being deassorted before the next active edge of the clock. So, here what it says that you are applying the this reset pin, this is the reset pin or the asynchronous input. So, it will change in this region, not a problem, but in this region it should not change. Okay. So, what it says that you have to make your asynchronous input stable, okay, and before the rising edge of the clock. Okay. How much time before the rising edge of the clock? Stable means that let us say you have a active high reset signal. So, your active high is applied here. Now, it is going to 0 from this point to this clock edge. How much time the asynchronous input should be stable such that new data coming to the clock edge can be captured by the flop properly, that is called your recovery time. So, means before the rising edge of the clock, your asynchronous input should be deasserted. Deasserted meaning that it moved from the high to low transition. This deasserted means high to low transition happens such that it will be the new data coming to the D pin can be captured by the flop properly, is called the recovery time. Similarly, the removal time is the time after an active clock is that the asynchronous input pin must remain active before it can be deasserted. So, there is also a concept called pulse width check. If the width of the pulses at the clock pin is smaller than the specified minimum time, then the clock may not latch the data properly. So, we should check the flip flop whether it is able to sample the data with the minimum pulse width for a given flip flop. If it is not satisfied, then the data will not be captured properly by the flip flop or the latch. So, the pulse width check, what it does? It has a minimum pulse width constraint. If it is satisfied, then the data will be sampled properly by the latch or flip flop, otherwise it will not be captured. This is the timing library corresponding to sequential circuits such as flip flop. This is the setup rising, and if you can see in this case your setup time is function of data slew, data transition time, okay, data transition time comma clock transition time, clock transition time. So, it will not depend upon the load. Why it will not depend upon the load? Because the fast latch, the master latch will see a same load all the time. So, it will only depend upon the data transition time and the clock transition time. First one, this is your data transition time, the first, then this is your clock transition time. So, now we will look into the basically different types of files used in VLSI physical design. Okay. So, this is very important to learn about before going to the VLSI physical design. So, what are the files are used inside the VLSI physical design that needs to be basically understand properly? It is very useful. First one is the LEF file. It is the library exchange format file or the technology LEF file. It consists of BEOL, backend of line layers technology. Whenever you have a process, you have FEOL and BEOL. So, the backend of line layers are the metal 1 and above. So, this LEF file will have all the layers information which is having metal 1 and above. The FEOL information is not provided. The reason it is not provided, because we are doing the routing in the metal 1 and above. I am not worried about what kind of transistor is there inside the technology node, because I only need the pin information whenever I am going to do physical layout. So, this place and route tools will use the metal pin information to do the routing. So, the FEOL layers are not provided inside the LEF file. So, it has the width and the spacing rules, and it has units of measurement of the LEF, which is basically the convert factors. It has database time, capacitance, resistance information. Okay. It has a database in micron, which means that 1 micron in LEF is with 2000 database unit. It has a manufacturing grid. Why this manufacturing grid is necessary? It is used for the geometry alignment or snapping the blocks to that grid, each of the cells and blocks to that grid. So, this is a sample LEF file, how it looks like. It has some of the informations like manufacturing grid information. It has database unit information. The bus can be shown, those informations are provided. you have a 32-bit lines. So, how that can be extracted in the LEF or Verilog, those informations are provided here. Then we have a technology LEF file, it has many more informations are there. Whatever I told you, the metal layers informations are there, metal 1, metal 2, via layer, all these informations is provided. It has routing, cut, master slice and overlap, those informations are provided. The direction, you have let us say metal 1 is one direction, metal 2 is another direction. So, this direction information is provided. The metal 1 pitch is provided, what is the default width of the metal is also provided. Basically, the spacings between the metal is also provided, the resistance value and capacitance value are also provided. Let us look into an example file here. Okay. So, it is the metal 1. Okay. So, it is a routing layer, obviously it is used for routing, and its direction is horizontal. Okay. So, this direction is horizontal, then the pitch is 1, okay. Then offset is 0.5, then the width of the metal is 0.3 and the spacing is 0.3. So, and it has a resistance information, it has capacitance information, all these informations are provided. Then you have VI information between the metal 1 and metal 2, all these are also provided in the LEF file. Here I am just explaining about the one metal layer, metal 1, but it can be available for all the metals available in that PDK. So, now we have basically site cell. So, it will say about the what is the height and the width of the site. The standard cell and the macro LEF consist of physical information such as height, width, pin of the standard cell and memory IP. So, this site cell is very useful for placing the cells in the placement, those will be placed in the on the grid. Okay. So, based on the site information, the placement grid is formed during the placement phase. So, now we will discuss about a standard cell LEF file. If you can see here, this the first one is the layout, whatever you do it in a layout editor. Okay. So, this is the layout editor view. This is the abstract view. So, what we are worried about, whatever I told you, these BUL metals are important. Okay. FUOL metals means below the metal 1 is not used, this poly, active, those things are removed, and this is the abstract view. Okay. This is called the abstract view. Basically, there is all the information to the physical designers is not provided because that is not needed. So, this is abstract view of the layout. We are basically look into the pin informations, okay, which is useful for placement and routing. This is the basically LEF for this inverter. If you can see here, you have VDD and ground pins are there. So, this is the VDD, okay. This is the VDD. This piece of information is corresponds to this VDD line. This is a VDD pin, if you can see here. Similarly, this is a ground pin. So, this piece of information is provided for the ground. Okay. Now, we have VDD ground is already described. Now, we have this is A pin, okay, pin A, okay, this is the pin A. So, this is corresponds to this pin, okay. Then we have the Y pin, this is the Y pin. So, this Y pin is provided here. Okay. So, this is the overall left view of this standard cell library. Now, we have another file called a DEF file. This is used for design exchange format. So, what is inside this design exchange format is basically design specific informations. Okay. It contains design specific informations like logical design data, physical design data such as size, shape, row, track, macro placement location, scan chain order, all these are there inside this DEF file. This is called the design exchange format. So, we have also units in database for micron, and die area is also specified in the def file. Now, we have another file called ITF file, interconnect technology file, which is comes with the technology PDK. It contains the layer information, the interconnect information, layer thickness, physical attributes such as conductor, dielectric layers, all these informations are provided. So, basically it contains the layer thickness and dielectric thickness, all these information, which is basically used by the RC extraction engine to extract the basically resistance and capacitance value in different forms. So, the different EDA tools use these files in a different compressed format to improve the run time of the tool and the accuracy of the tool. So, basically we can compress this information into different format to improve the run time and accuracy of the actual estimation of the well length. So, ITF file in short contains the interconnect parasitic information, which is used to calculate the interconnect delay in a physical layout in VLSI physical synthesis. Now, we will look into what are the files provided with the process design kit. The PDK stands for process design kit. It contains lot of files. So, here it summarizes what are the files there inside a PDK. It contains process and technology related files and data required for the layout, transistor level simulation. Those are provided by the foundry. Okay. Then we have some file, this is the first one. Then you have circuit simulation files. Let the SPICE file, the BSIM model files will be provided by the basically the foundry for doing the simulations. Then the third one is the layouts, standard cell layouts, transistor level P cell, parameterized cells. This is 3A. 3B is the transistor level schematic or the CDL. Okay. CDL will be provided. Then the 3C is basically layout related files for layout editors. Now, we will discuss about synthesis related files what is available in the PDK. This is the 4A will be tech file, ITF file, TLE plus, then the basically RC extraction files extracted from ITF file. Then the 4C will contain the DRC LVS related files, DRC, LVS, ERC, ESD, antenna, DFM rule checks in EDA specific format. It has also design rule manuals which explain the FEOL and BEOL rules with respect to the physical verification. It has EM electromigration, IR drop related files, top level wear bond, flip chip pad and placement rules, all these are also provided with the PDK. Finally, to summarize, the PDK is provided by the foundry, okay, and sometimes they write this PDK as digital design kit. Sometimes they foundry call this file as digital design file. So, you have synthesis related or the place and route related files such as physical views of the standard cells like the Milky Way and the LEF. Then we have this is the first one. Then the second one is your timing library, whatever we discussed extensively in the last lecture, how dot libs and dot db files. Then the third one is the GDS, this is the layout related file, which file you can extract to generate the layout, okay, in a layout editor. Then the fourth one is your standard cell behavioral and structural Verilog for simulations, okay. In the behavioral format is also provided for simulations. Then the fifth one is the standard cell SPICE and circuit files, that is also provided, and the sixth one is EDA specific standard cells, EMIR views, signal integrity views, all these are provided. In this lecture, we discussed about the characterization of the sequential cells in the standard cell library. Then we discussed about different PDK files available, which is used in case of VLSI physical design. For example, LEF file, DEF file and ITF file and other files. Thank you for your attention.